what you'd really like to do is just scoop out the energy in front of us, and the energy behind us would just shoot us forward. So that would be the way to do it.
And that's possible. That's not just a Star Trek concept, but you've seen...
No, we know, I mean, small effects, all of general relativity, for example, is based on these principles.
Tonight's guest is someone who is an expert in all these fields, and he's developing now a foundation for using zero-point energy as an inexhaustible means of replacing this oil economy and giving the world the energy it needs to live in the 21st century. He's also one of the originators of the remote viewing program that the CIA used for psychic spying, and that's a whole field of study as well. So his name is Dr. Hal Puthoff at the Institute of Advanced Studies in Austin. So you're the developer of basically these two divergent fields, the remote viewing.
That's true, right?
And then the zero-point energy. Is there any way that these two come together?
Well, it's not clear from a scientific standpoint whether they come together, but there's at least the possibility that, at least in the case of, say, psychokinesis, something like that could be cohering of this so-called vacuum zero-point energy. But it's not up to a place where we can, for certain, make a connection.
So zero-point energy basically is there's the vacuum or the void has fluctuations within that are energetic. They're vibrations. In the sense, the void is not empty. There is no such thing as a vacuum.
That's right. Originally, physicists thought that empty space was empty, truly empty.
Right.
But once quantum theory went forward, it was found that as a result of Heisenberg's uncertainty principle that there's always some jitter going on at some deep level. And so...
That's quantum theory. Sorry.
So it turns out that once quantum theory came along, it was recognized that this is an inherent part of nature. Mm-hmm. Interesting, at first, the enormous energy that was said to be in empty space seemed to be so enormous that physicists thought, well, maybe it's a mathematical artifact of, we don't have quantum theory quite right. Mm-hmm. But then an experiment was done. It was noticed that the light that comes out of, say, hydrogen atoms when they're excited, the theory of it didn't quite match the experimental data. And then they saw, when they took into account the fact that these atoms aren't sitting in an empty void, they're sitting in this sort of frothy, bubbly foam of so-called zero-point energy, that would actually affect their orbit somewhat, and then they could match theory and experiment. So the next step was, well, okay, this is real, but it's not very important. It's just minor corrections to atomic calculations or something. But then as time went on, it began to realize it played more and more of a central role. For example, the fluorescent lights, put electric discharge in it, excites the atoms, and then the atoms emit light. Right. And they emit light by a process called spontaneous emission. Spontaneous emission is sort of like the equivalent of setting a pencil on its point and then falls over. In this case, the atom is in excited state, and it's sort of like a pencil on its point, and it falls down and emits its energy. And at first it was just considered, Einstein had coefficients for stimulated emission as we have in lasers and for spontaneous emission, and it was considered separate phenomena. We now know, though, that spontaneous emission isn't so spontaneous. It's actually brought about by the quantum fluctuations. So the very reason we have fluorescent lights actually depends on the fact that empty space has this underlying quantum energy. When that idea first came out and was pressed forward in the 80s, there was an immediate test because it still was sort of skeptically looked at. So, okay, well, let's make a cavity. We'll put atoms in it. We'll eliminate the modes so there won't be any zero-point energy in those modes. And in that case, the excited atom should stay excited.
Right. They
built it, and it worked. They were able to actually show that if you reduce the vacuum fluctuations at the key frequencies that are going to stimulate this event to occur, they actually don't occur.
They don't occur. So you narrow the gap within these fluctuations. I mean, there's actually some control over the fluctuation.
Some control, right.
And this is what you're going for in your research, to develop a way of tapping into this energy.
Exactly. The first person to recognize that that might be a possibility was Hendrik Kasmer. He was a research director at Phillips Laboratories. And this energy is electromagnetic in part. And so just like if you go into a shielded room and you can't hear your cell phone or something because the room is shielding, we should have been in a shielded room.
Yeah, right.
Similarly, if you could have a region of space that you actually shielded, you partially shield these fluctuations and cause there to be a deficit in between.
Right.
And it turns out that when you do the calculations, that deficit results in the radiation pressure associated with the deficit trying to push the plates apart is not as strong as what's outside trying to push the plates together. The plates come together, bang, they hit, they create heat. And so there you've had some slight conversion of vacuum energy to heat. So that was the first sort of demonstration that it could be tapped, at least in principle.
And it proved to you that this is a possible unlimited source of energy that with the right kind of details or materials that you could somehow get to be an unlimited source.
That's right. When you calculate how much energy is in there in a region of space, Feynman and others have said, well, it's at least the order of nuclear energies, even in, quote, empty space. So it's a case of trying to find out how to collect the energy.
Well, how close are you to actually getting to this, I mean, like you said, like we talked about earlier, Edison, he experimented with 1,200 different elements or materials before he got tungsten to create the light bulb. I mean, how
in fact, in our proposals to our investors, we actually use the Edison story to point out, this may take a while. There are 4 or 5 techniques in principle whereby we see it might be doable. But we're still basically, anyone working in this field is still looking for the right engineering setup, the right construction to do it. It turns out that this effect in general, you get the most energy at very small levels, so it may require a lot of nano machining or something. And so, unfortunately, it's not like a big fire that you could just ignite macroscopically.
Well, are you confident that it will happen, that you will be able to get what you're going for?
I'm confident that eventually we will. What I'm not confident about is stating a specific timeline. I certainly hope it's within my lifetime, and I expect it to be within my lifetime. But
have you had remote viewers look and see what this substance is, or possibly, using some of these other areas to kind of tune in?
Right.
Because it's
actually, I haven't, although some have volunteered that they looked on their own and they sent me data, but it's still not specific enough.
You're looking for a material? Is that what you're actually looking for?
We're probably looking more, it's going to involve materials. It's also going to involve geometrical shapes, but also can actually involve the process. I mean, just to give you an idea, for example, the example I gave, plates coming together, that's a very mechanical thing. Right. Another case is to make arc discharges, sort of microscopic ball lightning. Right. And there you get a plasma that gets squeezed. Very similar. In other cases, you're setting up bubbles in liquids with sound waves, and then the bubbles collapse, and there's a possibility that that also would release zero-point energy. Schwinger, is a Nobel Prize laureate, wrote a number of papers where he felt that could be a mechanism that might show up in the sun and the medicine film. So all these different approaches are like wildly different from each other. You got plates, you got electrical discharges, you've got bubbles being created in liquid, others we've looked at involve gases.
So zero-point energy vacuum, it's a medium that things can travel through, right? The fluctuations are kind of like, let's say, water or water molecules.
We're sort of like looking at the electrical or electromagnetic equivalent of the froth at the base of a waterfall. Just a lot of random motion. That's why generally we don't notice that it's there because it's all random, and therefore any effect in any given direction is going to be canceled out by effect in an opposite direction. Although there is one case where we do notice that this energy is there, and that's in inertia, so-called, where if you're standing on a train that takes off with a jerk, you end up flat on your back. You know, what is it that knocked you down? It's actually ran into this wall of energy. It's very similar to if you put your hand in a pool and you go like that, you'll feel the back pressure in your hand. Similarly, if something tries to accelerate you through this vacuum fluctuation energy, the back pressure that knocks you down, in the case of the train, is actually this at work.
So the background fluctuations is holding mass in place in the form of inertia. Is that what you're saying?
Yeah, you hold it in place unless you apply a force, or as it turns out, unlike throwing something through the wind, if you're just going at constant velocity, there's no resistance either. It's only when something tries to accelerate you. Then there's a resistance proportional to acceleration. That's why you have to apply a force proportional to acceleration. Force equals mass times acceleration to accelerate, because you're trying to beat against a resistance force which is proportional to acceleration.
Right. So yeah, I think I follow you pretty much, but it's sort of like there's this medium that things exist in, but it's not quite this dimension of existence, right? Because it exists kind of within a void space. I mean, how does it apply to non-locality? You know, where, you know, let's say a photon here is affecting another photon there, and they say that instantaneously happens. That has to do with this medium of the quantum.
There's a connection, and that is that this vacuum fluctuation energy, which I'm concentrating on the electromagnetic part, actually there are other parts also, have all wavelengths and frequencies. So that means that not only is it wavelengths of a few centimeters or something, but there are wavelengths that are as big as the universe. So in that sense, we are not just figuratively or metaphorically, but we are literally in touch across the universe, because our atoms are bathed in this sea of energy that includes all these wavelengths, some of whose wavelengths stretch out, you know, across the solar system or whatever. But the thing you mentioned about this quantum correlation and non-locality is possibly somewhat different. We haven't actually been able to pin down. The chauvinists, CPE chauvinists among us think there is a direct connection. Right. But as far as the scientific community goes, that's yet to be shown, whether those are similar or different phenomena. And that has to do with the fact that there's a small school of people who think that you might explain much of quantum theory just by taking into account the effects of the vacuum fluctuations. And vacuum fluctuation theory, or zero-point energy theory, has been used to derive a lot of results that you would think you needed quantum theory for, but actually you can get it by this path. So the question is, well, can you get everything in quantum theory by this path? For example, non-locality. This is still a relatively new area, pushing into those areas, so we don't know the answer. And the whole space-time thing where you talked about contracting space in front of a ship and then having it travel at warp speed, that has to do with this background fluctuation. That's right, having change in the density, as we say, changing the polarizability of the vacuum is another way of looking at it. So you're accelerating through the vacuum, right? Because when you say you're accelerating within this quantum fluctuation, it has an effect on that background field, right? I mean, did you say that? Or that is certainly the case, because it's essentially pushing aside the vacuum fluctuation to some degree, and that's what's causing the resistance that we call inertia. But again, for example, in the case of the Casimir plate, which is a simple example, you've got a depleted area of zero-point energy here, so you've actually got forces that will push you in that direction down into this depleted region. So. But how would you actually contract space-time to do that? I mean, what effect could you put out there to have that? Well, we know from switching over the general relativity side of it that you can look at the equations, whether you're using standard general relativity or some of the other approaches to general relativistic type effects, and very strong fields, strong masses. I mean, the mass of the Earth affects the space around it, which, thinking in terms of zero-point energy, is affecting the distribution of zero-point energy.
So if you go to that equation, F equals ma, where the mass times the acceleration equals the force. If you create a force, you can generate a mass that would have an effect on space.
We might generate a force that would move a mass, start to accelerate it. Or, I mean, what you'd really like to do is just scoop out the energy in front of us, and the energy behind us would just shoot us forward. So manipulating the density or the vacuum polarizability or the space-time metric, all those words, relationship with each other, that would be the way to do it.
And that's possible. That's not just a Star Trek concept, but you've seen...
No, we know, I mean, small effects, all of general relativity, for example, is based on these principles. And we can calculate, well, gee, if only we had so much energy,
right.
And then we could make this big effect, we could power a spaceship and so on. It's just that we don't have the engineering tools to do it right now. And frankly, those of us who are working on it think there's still something missing in the theory, because it's so hard to do. We don't see that it could ever really be done, and yet, you know, maybe there's some evidence that there are spaceships out there that don't belong to us, belong to somebody else. Well, in that case, they must have gotten around it. So there may be some unexpected factor that could suddenly cause a resonance to occur where with a lot less energy you could get a big effect.
Right. And that usually happens in science, that they back into a solution instead of, you know...
Right, and usually it's even by accident. In fact, even though we think we're smart enough that we should figure this out, we have something we call the Maverick Inventor Program. And the idea of our Maverick Inventor Program is that as smart as we think we are, it may be some guy in the garage who's half crazy, who stumbles across something. Nobody will pay any attention to him. He doesn't have good instruments because he doesn't have enough money to buy them, so his measurements are all messed up. But nonetheless, he may actually stumble on something. So who's going to pay attention to him? The academics aren't, the corporations aren't. So we have our Maverick Inventor Program where we put out the word on the internet and elsewhere saying, you know, if you think you have beat the system, if you think you've come up with a novel energy source or a propulsion source, bring it to our laboratory, we'll investigate it. And so we've investigated many things brought to us. They all go up on the website, so great gory detail. You can see what we've learned.
Well, you know what I've thought, and you could use this if you want, is that somehow inert gas represents a kind of boundary to this dimensional space. I mean, electronic, with the electrons filling up certain shells. So there might be some kind of way to get beyond that boundary that inert gases represent in order to access some of the in-between places in the quantum fluctuations. Does that make sense?
Well, it turns out that some of our best experiments that actually have shown what we call over-unity energy generation have involved striking spark discharges in noble gases.
Right.
And as a result, we've actually seen some evidence for energy generation or energy conversion. That was the good news. The bad news was that it was at the nanowatt level, and the devices were immediately corroded and didn't last. And then all attempts to scale up those particular devices, it turned out that the losses scaled up faster than the good effects. So even though we have something like 7 patents that have been patented, and the patent office bought off on our claim, which was these were devices to convert vacuum fluctuation energy into some other form.
Right.
But nonetheless, we haven't actually come up with the right connection yet.
Right. Well, philosophically speaking, if we can just kind of, you know, relax a little bit into that, if let's say we do come up with this source that we tap the void, the free energy that's out there, doesn't that change the whole social psychology of a society that says, yes, there is a free lunch? I mean, we're going to have a, you know, huge ramifications, I mean, psychologically.
Oh, it'll have actually a lot of ramifications, sociologically, psychologically. For example, from the geopolitical standpoint, when you have an oil economy, you're tied to the geopolitical sources.
Right.
This energy, which is everywhere, is in that sense more democratic,
right?
Because it doesn't matter where you are, you could in principle tap it. It also could, in the long run, as people really have soak into their philosophies, affect things in a way I've thought of, and that is our entire physics structure is hierarchical. We have the sun; it provides energy to the earth, it grows the plants. We obviously have a hierarchy of where we as beings and individuals get our energy from.
Right.
On the other hand, this is not a hierarchical process. It's a broad scale process, and so it's like really a conversion from a hierarchical attitude toward a whatever you would call it.
Everybody is
right.
free and accessing.
Right.
Because isn't science always sought nature as an ally? Isn't it the basis of science is to kind of, make our life here more comfortable and to make...
Yes, but it goes through phases where nature is an enemy to be conquered.
Right.
And then, nature is something to be accommodated to and interacted with. And but generally speaking, we see it going in both ways, obviously. We have appliances that make drudgery in life easier, and then we have hydrogen bombs.
Right.
So
it's like fire,
Exactly.
Yeah.
So similarly, I look on zero-point energy as being like those. They're a tool, but in the end, it's what people do with it that counts.
Right.
And unfortunately, it would appear that our sociological and ethical levels are barely, if at all, keeping up with our technological prowess.
Well, maybe that's what consciousness itself is waiting for, to have this invention or this discovery.
Have enough of a challenge to say, okay, we're going to really have to get our act together. We're not going to handle this.
Right. I mean, was Tesla onto anything? Because the stories that said you could stick one of his lightning rods in the ground and get energy. Is there any truth to any of the Tesla devices?
Well, certainly Tesla was a genius.
Yeah.
No doubt about that. I mean, it's still hard for electrical engineers to go through school to really get their mind around how some of his complex AC machinery operated. I mean, there's no doubt he's a genius. And he also had a strong intuitive feeling. This was before quantum theory. He made the statement, which I can't quite remember the exact quote, but he said he felt that space was full of energy. If it was static, it wouldn't do us any good, but if it was dynamic, we would yoke man's inventions to the wheelwork of nature, quote, something like that. And of course, now that we know that zero-point energy, vacuum fluctuation energy is dynamic, it does fill all of space. If we look back and say, well, his intuition was right, although he didn't have the details down. Now, as far as the stories of the various devices he made, some of them, like his attempt to generate energy with his antennas that would then propagate around the world.
Right.
It makes some sense, but it's not clear that it really would have worked the way he thought. There's some more urban myth kinds of things that, he built one of these free energy generators and ran a car, but no one's been able to really pin down. That's not in his patents. No one is really, it's basically anecdotal stories, so it's hard to know just how far. I mean, you're looking at a genius, he comes up with things you don't come up with, and a lot more, and then you say, well, since these are true, should I believe those?
Yeah.
And it's just hard to evaluate until we can cover the same track. But there are a lot of people interested in Tesla.
Well, the same thing could be true of Newton, who, after developing his laws of thermodynamics, studied alchemy for the rest of his life, and maybe he was onto something, or maybe he was crazy.
That's right.
Crazy. But, in reading some of the material, there's something called the cosmological constant, where the relationship of the electron is somehow related to the size of the universe.
Yes, and some of the zero-point energy modeling that I and my colleagues have studied, and we did come up with some ways of relating the size of the universe to, quote, the classical size of an electron. And that relationship comes out of zero-point energy modeling. So we're pursuing things like that. Right. In that sense, zero-point energy modeling at the intense level we're pushing it is like trying to get a step deeper than the usual equations and usual effects. So some of it still needs to mature before we're sure we're onto something. But
I mean, could the universe itself be an electron in some greater, vaster, unfathomable?
Well, it has been talked about the fact that the universe, when you look at the numbers associated with it, could itself be a black hole. We might be in a black hole.
Yeah.
And who knows how many others there are out there. Actually, this idea that you just mentioned about, well, couldn't we be like a small component in a much larger, there are a lot of serious theoretical work going on now by cosmologists about the possibility that our whole universe is just one of many.
Yeah.
Lindy at Stanford, is Russian, who's now there at Stanford, is one of the most respected cosmologists. He's of the opinion that, well, this universe got spawned. There's no reason why another one couldn't. And today is no better than yesterday, so maybe it's like a fractal tree and the universe is being spawned all over the place on a continuing basis. We just happen not to be connecting up with them. But then even that theory has gone a step further, where now people are talking about, yeah, but maybe sometimes these universes run into each other and then you have a big release of energy, and maybe that's behind some of these mini big bangs or quasars or whatever. So these days, cosmology and astrophysics is outstripping science fiction so fast you can hardly keep up with it, and the theories are proliferating. And in the old days, if you had a wild theory, it might be shunned, but these days the data is coming in so fast and we have so many inexplicable phenomena going on that basically it's okay in physics now to have really wild theories that you're going to try to check against the data.
Well, and what's one of your favorite inexplicable theories? What do you really draw to?
Where the energy from quasars comes from, or gamma ray bursters. They're humongous amounts of energy. There was a gamma ray burster just a few years ago that basically, as far as we can tell, released more energy second only to the Big Bang, so-called. And so accounting for that is difficult. And there are actually a number of papers that have been published on the idea that maybe it was. In fact, there are papers called Casimir collapse of supernova, indicating that maybe some vacuum energy is being released in some of these phenomena.
Obviously, more that we don't know than we do know. It's always been like that.
I mean, now it's really getting down to the embarrassing point where we recognize that 4% of the universe we can account for, and the other 96% is in dark matter and dark energy, and we don't know what either of them are.
Right, and there's all the string theory and interdimensional and multi-dimensional.
Yeah, I mean, it goes on and on.
So, I mean, there could be something behind the zero-point vacuum energy there. I mean, what it seems like in some of the other literature, maybe some of the metaphysical literature, is there's a grid that then gets coherent that lines up the quantum fluctuations. Do you have any evidence of some kind of other dimensional type grid that's behind the fluctuations?
In my case, I happen to have done a particular calculation and published it actually in Physical Review A, where I took a different tack, and that is, you got all these charged particles, all these atoms, electrons, and so on, they're all jiggling around in the zero-point energy C and radiating away, and then any given atom is caught in the radiation pattern of all the other jiggling particles. So I did a cosmological calculation and found that it appeared to be the electromagnetic equivalent of putting a speaker by a microphone and getting a squeal. The particles are all radiating and causing the other particles to jiggle, and then their jiggling is a feedback mechanism that causes them to radiate to cause the first particle. And so this thing is like a self-perpetuating mechanism, and it turns out that the frequency distribution of zero-point energy goes as the frequency Q, frequency to the third power. So there's more and more energy in the higher and higher frequencies. And this particular calculation predicted that cubic frequency distribution. So in my modeling, I don't need any extra dimensions. But I know there are other people who consider that maybe zero-point energy is something pouring in from another dimension. It just happens not to be the tack I'm taking.
Well, there's something behind it. There's another more subtle layer. Let's say there is this, foam that exists, and then something is generating the...
Well, yeah, actually, this is an area that I and my colleagues at the Institute for Advanced Studies are looking at right now, because even when you say, okay, I've got zero-point energy, say, well, what exactly is that? Well, it's electromagnetic. Well, what do you mean it's electromagnetic? Well, it's got electric fields, it's got magnetic fields, and waves. And okay, well, what is an electric field? A wave in what? Right. And so, in some sense, unless you just want to draw the line and say, yeah, it's mathematically it works, I'm not going to worry about it. There are still the questions, well, obviously there's something even deeper than that, because we're not describing what the zero-point energy electromagnetic waves are waves of.
Right, exactly. And what I'm sort of getting to is this whole idea of consciousness, you know, where you're saying that you can't really shield, or you've been able to shield some of the zero-point energy field, but you couldn't shield it from a remote viewer, you know, so like consciousness somehow is traveling in some medium or a part of some non-local aspect that's even beyond these fluctuations.
It certainly has got to be the case. I mean, these fluctuations are handleable by normal physics, and they appear in the textbooks and so on, but no one has a model for how something like remote viewing could really work. So obviously there's a lot more going on, even beyond what we can model.
Right, but there probably is a science, or there's some maybe more subtle medium in which consciousness then can travel, or...
It'd be reasonable. I mean, certainly as a physicist, I assume if it walks, it's physics. So if it travels even spiritually, it's physics. But, you know, it's interesting that it used to be ages ago, religion was the big thing.
Right.
And then at a certain point in our development, we carved out a piece of religion and called it philosophy. Mm-hmm. And then we carved out a piece of philosophy and called it natural science. And in that transition, I've always marveled at the fact that what was alchemy then became chemistry. Right. What was astrology became astronomy. What was metaphysics became physics. And this always gets to go to my psychology friends. What was demonology became psychology. And that process was a process whereby we're trying to get rid of the subjective element, make it totally objective. Right. Unfortunately, in that process, we somewhat threw out some of the baby with the bathwater, but I think it was a necessary step to go through to get the subjective element out. Right. But now that science has gotten its legs and it's somewhat strong, it's beginning to reincorporate. So, for example, we had astrology saying, you know, things depend on the stars, and we know you have chemistry, there's no subjective factors. Now it's been recognized pretty much by scientists who are open-minded that there is a so-called Mars effect. That is, people born under the sign of Mars happen to be, you know, fill up the books for athletes. And similarly, numerology, which then became mathematics, so the magic of numbers kind of went away. But now that we have mathematics, we're beginning to realize that principles like supersymmetry are kind of saying there is a magical aspect to mathematics. And similarly, you know, you can go from alchemy to chemistry.
But even quantum theory says the observer, you know, is maybe the center that affects everything around it. So, I mean, just by having the observer affect something means that, you know, consciousness is sort of a center point of the universe. Each individual consciousness, let's say, is a center of totality. I mean, that's how I see it.
You know, certainly, and some physicists have really pressed that point home. Eugene Wigner was especially pressed that point that really, as long as we're leaving consciousness out, we're making a mistake, and consciousness is somehow involved in the observation process. And certainly, from a physics standpoint, any measurement which yields information to an individual, obviously somewhere along the line had consciousness involved, so it's a case of, well, just how much was it involved? And John Wheeler, who's one of the icons of physics, has made a big issue out of, you know, that it's a participatory universe is his phrase, rather than just a remote observer.
Well, if it is participatory, then we have an effect on the quantum fluctuations. I mean, wasn't your initial going into remote viewing a field based on a quantum understanding? You told a story about that.
Right. I was interested in whether quantum physics could be extended to account for living processes. And at that time, there were some ideas kind of floating around, and so that is what sort of got me started looking at consciousness issues and doing that experiment that ended up with the government showing up at my doorstep.
Right, with Ingo Swann. But you also told a great story about how you started to investigate levitation.
Well, that was later on when we were looking at the literature about so-called psychokinesis. And in fact, we weren't getting any in the lab, really. Well, we did get some magnetometer experiments. And
with mental projection.
Where basically someone sat there and we had sensitive magnetometer, radiometer actually, and on a random schedule that was spit out by a random number generator, the person had to make something happen or not, and we got statistically significant evidence. But they're always really small scale effects, so that's when I did think of, well, you know, we have a literature where people are claiming that, you know, we have levitating saints or whatever. So I decided to look in the literature. I wanted to see the descriptions of these phenomena, to see if there's some physics there we can learn. And I must admit, I started out skeptically, as well as probably maybe the church bragging about their magical people or whatever. When you actually go into the records, it turns out it wasn't that way at all. It turned out that somebody out in the boondocks was levitating. It might be a very profane person. And so, in fact, at the time, the church went out to debunk it. Well, there's a person apparently floating, so you can't say it's not happening. So the next line of defense was to take very careful notes to show that there were certain subtleties and nuances that meant this was diabolically inspired, not God-inspired. And in those notes, a physicist recognizes description of general relativistic kind of phenomena.
Like what? Like this?
Well, like for example, the person might rise vertically and then swing horizontally. By the model of the day, which is that some invisible demon had picked the person up, you'd still expect the hair to hang down, the dress to hang down. In fact, the hair would hang down parallel to the body, and the dress would hang down parallel to the body, as if they were in a space warp. And if somebody else got too close, they could get caught up in it. Another aspect was
if someone got too close to their field, they could get also.
They could get.
And that's in the literature as well.
That's in the literature as well.
And you wouldn't expect that.
You wouldn't expect that, especially by the priests who. And so, but there are other more subtle things. For example, it was described that the people's faces would glow like molten metal, and you say, well, that's strange. But it turns out that you've probably heard the term redshift. Heavy gravitational stars and so on, the light comes, it's redshifted. Well, in an anti-gravity condition or a levitation condition, it would go the other way and you get a blue shift. So you could easily imagine that, okay, if somebody's in a levitated state, then the heat spectrum that you don't ordinarily see might blue shift up in the lower part of the visible spectrum, and you would look like you were glowing. And so there are little subtleties like that, and I look at it and say, well, no, they didn't know about general relativity, so they didn't know how to make this up.
Right. So what do you think they were doing to get to those states? I mean, what internal...
Well, this, the only thing I can imagine is that they were affecting the space-time continuum. And that probably means, where is the energy to do that with? Well, the vacuum fluctuation energy is there, so they must be cohering the vacuum fluctuation energy. And so actually, it was because of that I started looking at a vacuum fluctuation model for gravity, and then eventually inertia. And so some of that was actually inspired by saying, okay, well, they must have cohered the vacuum fluctuation energy, so it must be that gravity is somehow a redistribution of vacuum fluctuation energy. And then I found out that, in fact, Sakharov, a famous Russian physicist, dissident and so on, was actually the first to come up with the idea that, okay, we've got general relativity, we've got Einstein's equations, that's all fine, but where do these equations come from? They just say if you have mass here, or energy here, or space gets warped here, but this is just a mathematical equivalence. Where does it come from? What's it due to? And so he took it a level deeper, and he came to the conclusion that it was, in fact, a redistribution of vacuum energy.
So if someone has the ability to mentally cohere the vacuum fluctuations, then they could levitate. I mean,
I would think that would be the case.
So
I keep waiting for somebody to show up and can do that because I have a whole list of experiments.
Well, can Ingo Swann? I mean, you said Ingo Swann affected the quark receptor.
Hard to pin down exactly what mechanism was going on. He was affecting a very sensitive magnetic device. I need something to test out the zero-point energy theory. I would need something a little more robust.
You need some,
I think.
But have you been able to measure? I mean, you said people could move these magnetometers, but has there been any measurements of the psychic kinetic energy coming off of people? Yeah.
Not really. I mean, people have claimed to make some measurements. Sometimes I know in another laboratory where people would claim to psychokinetically cause a magnet needle to rotate. Then they would leave, and it was found that if you put a new compass in there, it would rotate. So the structure of the space was somehow restructured to some degree, and it only faded over hours. Now, I'd like to get in there. If we had really good devices for measuring zero-point energy and had a long enough time, it'd be possible to make those measurements, but no one has done it.
But this whole idea of consciousness that somehow is beyond the zero-point energy field and also maybe beyond space and time, like you've done in some of the remote viewing experiments, sort of implies that, we have some key within us to controlling reality and the fluctuation.
Certainly what we saw in the remote viewing was that people could do things that as physicists we couldn't explain, especially the future viewing of future events. I mean, that really wipes out most theoretical modeling. Even models that involve the possibility of forward and backward propagation of light waves still can't handle somebody describing an event that takes place in a week or something.
How would you, let's say if you were to hypothesize, how would you, in physics terms, or maybe some far-out physics, explain it? I mean,
well, one depressing way to explain it is that it's all cast in concrete from here to infinity or whatever, and we're just marching through the slideshow frame by frame. Everything, there is no such thing as free will, it's all cast. And so somehow somebody finds some tricky way to jump ahead a few frames and see what's happening. That might imply that, we don't have free will. So that's actually, you can get into sophisticated arguments where you can actually make all those things kind of work out, but it's a tough way to hope.
Well, what about but they weren't always right about, forecasting the future.
That's right.
This whole idea about parallel universes or each moment there's a split in the possible futures that can happen from this moment on. It depends which path we take.
In fact, to show how sci-fi physics has become, there is a serious theory. By serious, I mean it's published and no one can hit holes in it, called the multi-worlds interpretation, the many-worlds interpretation of quantum theory, which says that at every instant of all the quantum possibilities, everything that could happen does happen. And so there's a you that just said this to me, but at some quantum level there was a you that decided not to say that, to say something else, and he's going off. And so, but it's just so seemingly absurd from the usual viewpoint. I don't think any physicist really believes that all possibilities are in fact unwinding into the future.
But they've been able to mathematically prove that that's possible.
Well, they've been able to mathematically prove that if you have that physics set up with that understanding, it doesn't violate anything we observe, because it just turns out we're following one of the tracks. So it's like a theory you can't disprove.
Right.
I don't think anybody, no one's thought of a way of proving it unless you actually get access to alternate realities. But I'd have to say no physicist really buys it. But it's in the book, says when anyone lists various approaches to quantum theory, that gets listed because it can't be disproven.
Well, you've in your thinking though have been through many levels of openness, right? I mean, you came to remote viewing very, thinking that it wasn't possible, and you expanded.
Not only did I come to remote viewing thinking it wasn't possible, 13 years into the program, every time I went in to do a session with a remote viewer, I would ask myself, how can I be doing this? Why am I here? This can't possibly work. Mm-hmm. I have all the same resistances bubbling up, and then there'd be some spectacular result, and I'd say, I've got to face it. And
so, I mean, we do have to reevaluate our whole understanding of consciousness physics, and I bet you yourself even remote viewed, right? I mean, you were also...
No, actually, one of the conditions of the program, of the government funding, actually from people at CIA who started the program, was we learned from the LSD days the experimenters should not get involved in their experiments. So we will let you have this remote viewing program on one condition, and that is you never yourself remote view. So, I mean, looking forward to polygraphs and so on, we had to be careful, so we didn't.
But now that you're out of the program, have you tried it?
Occasionally for fun.
But there is something to it. I mean, I've tried it, and you do get images flooding into your mind, and it's coming from somewhere.
Yeah, well, I mean, certainly, as we saw, even when you've got a remote viewer, you've got an interviewer, and you have some target, you don't know what it is, and the person comes up with something that he knows just can't be right. The interviewer is sitting there really disgusted. He knows what the person is saying can't be right. They both try to get rid of this image, start from scratch. It still keeps coming in, so finally they give up and put it down. And it turns out to be correct. So obviously the information is there, and it has a certain robustness that you can't just discount.
So taking it all together, the quantum fluctuations, the remote viewing, I mean, there probably will be a place where they converge in the sense that consciousness is somehow a key element in all these phenomena,
Yeah, I mean, as I say, as a physics chauvinist, okay, I've got the physics I know, I've got some advanced physics that we're pushing, I've got this island of remote viewing, I've got this island of consciousness. I know they all go together because
they're all pieces of
the universe. And really, if we had truly the physics of the universe, then everything would be in there. So the fact that everything isn't in there, we know we got a lot of work to do. But I make myself feel better by realizing that there's going to be a 26th century physics and a 32nd century physics. And whatever that physics is, they're going to look back at 21st century physics and say, oh, how could they believe that stuff is so limited, is so primitive. So clearly, as time goes on, we're already getting little snippets of connections between these things, but we really have a lot of work to do. I have to say, nothing makes you more humble than being a physicist facing the realities and you realize you can't stitch them all together yet.
But you have an open mind, which is the best thing about you.
I keep an open mind, but hope my brains don't fall out.
If it's too open. No, but I mean, your work is connecting these dots, and in particular.
Yeah, that seems to be my destiny in life. On the physics stuff, I'm on the edge of it. Obviously, in the remote viewing, we're on the edge of consciousness things, and some people just sort of have a makeup that if it isn't out on the edge, it's boring, and so I happen to be one of those people. But there are more and more these days.
Well, it's great. I mean, it means we're in a more open society where more breakthroughs will happen.
That's right. And also, even just one thing that does feed it is our technological prowess and our technological progress are opening up things faster than we can account for. I mean, if something comes down the pike one day at a time, you can kind of incorporate it and say, okay, that's fine. But now stuff with our super telescopes, Hubble, whatever, they can let us look at back in time, edge of the universe that we can see. And the microscopes are looking at quantum phenomena where we now make lasers out of single atoms.
Wow.
I mean, this stuff just goes on, and so the stuff is coming in such a fire hose that any physicist realizes that, he's not able to integrate all this stuff. You know, we really have a long way to go. There's a lot of data now. We're in data overload to try to pull it all together. But on the other hand, that's the fun of it.
Yeah, that's the exciting times we live in. So, I mean,
Right.
Thank you for all your hard work. And,
well, I actually get paid to do this as a living, so I'm really a lucky guy. I mean,
you are. You get to think of new ideas.
Yeah,
And, I mean, it'll be phenomenal the day you say, yes, we got the answer to how to tap into the zero-point energy field.
Yeah, recently I was on a DoD panel in January of this year where we were tasked with looking at how do we accelerate movement from a fossil fuel economy to a hydrogen economy. And so I got to spend one afternoon presenting what we call the wild card scenario, and that is, suppose tomorrow we suddenly discovered zero-point energy as a source. So we had to sort of war game, you know, well, how would we handle this? You know, what would we do? How would we announce it? Who would be in charge? You know, would this be primarily government-driven? Would it be primarily corporate-driven? I mean, these are really complicated issues, and they had a magnificent computer integration system where all these ideas went into this elaborate expert system, and it was trying to, you know, come up with an optimum path for how you deal with this. So, yeah, it could be a big event.
Well, it could be Nobel Prize material, I think. But as a humanist, you also have a perspective on just the kind of immediate situation, how it affects people in their everyday life. You know, I mean, it would be. It would probably do something to religion, I would think, right? The belief system in, you know, a god or some of the heavy belief systems. So,
well, certainly to find that we're all interconnected, we're all part of a fabric of space-time energy.
Right.
It'd be harder and harder for an individual to maintain that he was an isolated unit.
Right.
And so the more and more we find that we are connected into the cosmos as a whole, finally, in my way of thinking, it'd finally come down, we would end up finally with a unified view in which energy and information and process and dynamics were all an integrated whole. So it would affect all of our philosophical, religious views and our economic developments as well.
A whole new world. Do you have a question, John?
One question now. String theory. I bring that up because underlying that you're assuming 11 dimensions based on a mathematical construct. Do you feel that's a rational way to go, or is that artificial? Should we be searching for other dimensions? If so, how in the world can we deal with it?
Well, string theory is an interesting challenge, and it has made the headway it's made because the mathematics that have been developed to look at, well, what would it be like if we had an 11-dimensional universe or whatever, have predicted some unifying aspects of electromagnetism and gravity and so on, even accounting for particle structures and so on. So on the one hand, as a mathematical tool, it keeps kind of spitting out some things that we know are true and hadn't really thought of how to account for before. So it's like you can't exactly say, well, I'm just not going to bother thinking about that. On the other hand, it's also one of the disasters of string theory. It doesn't look like there's any way to actually do an experiment to prove whether or not strings, the string theory way in the 11 dimensions is a way to go anytime soon. And so that means you can really run amok with mathematics and maybe not get anywhere, but it wouldn't be possible to tell if you were getting somewhere, whereas most theory you can sort of go out and test it to see. On the other hand, there are certain implications of it that say, well, there's some experiments that, well, maybe we could accomplish something in the lab. So one specific prediction of some of these multidimensional theories is that Newton's inverse square law when you think about, well, where does an inverse square law come from? It comes from the fact that if you've got a sphere here and you imagine lines of energy or gravitational field coming out, as you go to bigger and bigger and bigger spheres, the area grows as the square of the radius, and therefore the density of lines coming out through is going to drop as a square. Then you say, okay, but suppose I had not this two-dimensional sphere, suppose I had a three-dimensional sphere and spanning in a four-dimensional space or whatever. Well, then it turns out you wouldn't get an inverse square law. You'd get something else. You'd get an inverse cube law if you had access to another dimension. So people are actually going to the trouble to do experiments in laboratories. Say, okay, well, let's measure Newton's law at micron distances, millimeter distances, micron distances, and if in fact these other dimensions are there when we get down, and if they're not too far away, or maybe they're kind of big, we could actually see an experimental result where we had a deviation from the inverse square law at very tiny distances. So people are doing that at those experiments. They've gotten down, I know they've gotten down to millimeters. I don't know if they've gotten down to tenths or hundredths of a millimeter yet. So those areas where we say, okay, maybe we're right on the edge and we can determine whether there's some extra dimensions here, people are doing experiments. So it's too early to say about string theory. Certainly some of the most elegant mathematics, Brian Greene, whatever, I mean, it's gorgeous stuff from a mathematical standpoint. And so the only thing is, okay, it's great aesthetics mathematically, but is it real? Well, we'd have to find out.
One of the promises was, I thought, that you would be able to predict the force or the size of a particle based on the size of other particles. In other words, you would have a general means of calculating the force and the size of all the elemental particles in the universe.
Well, this is the point where all theories are foundering we have these particles, electrons a certain size, certain amount of charge. Well, here's a proton, so here's some quarks, they've got some different charges and masses. And you say, okay, if you're so smart, if you've got a theory that, why don't you predict all these? Well, we can't predict a single one. We don't have a theory that yet necessarily looks like it's going to be successful in predicting it. And now that we're into quantum theory, where everything's jiggling around anyway, you begin to worry whether it's even possible in principle we could ever predict something very accurately. So,
or whether there's any mass at all, but just charge, right? I mean, isn't there that whole theory? There's only.
In fact, my colleague at Institute for Advanced Studies, Michael Ibison, is specifically working on a model of massless charge,
right?
Where it's just charge and fields,
right?
And then a mass, the appearancy of mass comes out at a higher level as just a consequence of the fact that mass does not exist as a fundamental thing, but only as kind of a byproduct.
Right. Then you get into the Hindu thing that this is all illusion, and what they say, it's all right, and this is just forces anyway, charge.
Well, even some of the so-called ether physicists of the 1800s had come to the conclusion that there is only one thing. It's sort of like water in the bathtub. You've got waves that go back and forth, you've got vortexes that go down the drain, but it's all made of water.
Right.
And there's nothing other than water.
Is that true? Is in your, with research, is that possible? That it's all just made of one thing? It's all
made of one thing?
Yeah.
I wouldn't reject it, and I tend to have a sort of subjective leaning in that direction. But whether it's true or not, I don't know. I mean, we have to get to that point.
Right.
See.
I mean, wouldn't a proton qualify? A photon. Because a photon can go in any direction. It could become mass.
Photons are very complex, because when you think about a photon going through space, it's got electric fields, it's got magnetic fields, it's got spin. So right away, even something as simple as a photon turns out to be complex enough that you try to figure out, well, why is it circularly polarized, or why is it this, or why is it that? So people have said, well, maybe particles are trapped photons. Well, that may take us a level deeper, but no good model has actually worked out yet. But then you say, okay, well, a photon might be trapped neutrino-antineutrino pairs.
Right.
People have thought of that. Well, then the neutrino-antineutrino pairs might be vortexes in a superfluid vacuum.
Yeah.
And then, well, the superfluid vacuum, just like it turtles all the way down. I mean,
Right. So it's all possible, but you have your focus in one particular direction.
yeah, I actually, even though I'm a physicist, I'm a very engineering-oriented physicist.
Right.
So I have a lot of focus on how can we make something work, do something with it. So yes, I dive into a deeper level of physics than many physicists do, but it's not that I'm trying to get all the way down. It's that I want to go a level deeper, find out what the options of maybe doing something with this level are. And so I'm focused on actually arriving particularly at energy and propulsion for space travel.
Well, it's great. It's great work you're doing, and it's an exciting time to be in this field.
It is. And there's broad-scale interest in government and corporations and foundations. I do a lot of consulting for all three, and there's interest everywhere in new ideas.
Actually, I mean, I had a question. If the speed of light is a certain thing, and it seems that thought is beyond that, I mean, is that sort of the next step, and that thought can penetrate into something that's electromagnetically impermeable?
Well, it'd be nice to find out. There haven't really been any good measurements of the speed of thought. We tried once, actually. One of the experiments we did, as I say, our remote viewers always get bored with the mundane tasks we're giving them, and so Ingo Swan and another person by the name of Harold Sherman decided they wanted to look at Jupiter before the NASA flyby. And so we set up a time and got the tapes rolling, and they viewed Jupiter. And especially Ingo, this was before the Voyager flyby, he found rings around Jupiter. And he said, well, I wonder if I'm at the wrong planet. I know Saturn has rings, but I'm trying to get to Jupiter, but I'm seeing rings around Jupiter. Don't seem to be very strong, but that's what I see. So I said, okay, well, that's the way it goes. And then Carl Sagan happened to come by the Institute, and we said, oh, we'd like you to look at this material that's generated by a remote viewer. And, he's a very skeptical kind of guy, and he read it. He said, well, I only see two things in here. There's either stuff you can get out of any encyclopedia, or there's stuff that's just dead wrong, like rings around Jupiter. So when Voyager got there and found out, in fact, there were thin rings around Jupiter, I thought, well, gee, this is really great. So what this led to was, okay, well, if we can get good data from that distance, maybe we have a chance of measuring the speed, because it turns out that moons of Jupiter go into eclipse at a certain time, and as it turns out, the almanac only predicts it to within a few seconds or even longer than that. So we can eliminate the possibility that somebody reads up the almanac in advance and tells them. And so the idea is, okay, are they going to see the eclipses of the moons of Jupiter when the astronomer sees the eclipses, which means it goes the speed of light, or are they going to see the eclipses instantly before the astronomers see them, which means thought was like sort of infinitely fast. So we did, it was a casual experiment. It wasn't really pinned down, but anyway, it appeared that he was seeing it instantly. However, you take into account precognition. Say, okay, well, maybe he precognited when the eclipses were going to occur and then reported them now. So you soon realize that it's really difficult to, if you take into account the possibility of precognition, it's really difficult to do an experiment to measure speed of, let's say, remote viewing or...
But the quantum field says there's no past, present, future all happening at once anyway, right?
Well, I know that's a phrase people use. I guess it's some, I guess I don't buy it.
But
on a more physical level, like the way birds fly in a flock as one, and that it seems like the thought patterns are happening instantaneously as opposed to any kind of lag time between them.
You know, if I hope that as time goes on, people will get more open to evaluating these things, because in fact, that could be checked. A high velocity or high speed filming of, say, birds in flight, to the point where you could measure how quick was it that they were in alignment. I mean, there'd be other factors you have to take into account, that maybe there's some other subliminal signal, like, okay, on the count of 3, we're all going to turn right, and then 1, 2, 3, then we. So, you know, it wouldn't be a trivial experiment to do. It'd be an expensive experiment to do. You have to have somebody who's smart, knows how to design an experiment, knows that this is going to have many factors and not going to be trivial to do. Somebody's going to have to pay for the time and the effort and the computer time to analyze the experiment. And nobody's done it yet. So I don't know of any experiment about speed of consciousness.
Isn't there Bell's theorem that says every point in time and space is right next to every other point in time and space? Do you know about that?
It's that in certain well-defined, pristine experiments, you can show that there are non-local connections between atomic particles, photons, and so on. So non-locality is there. But when time you extrapolate up to, say, human being interacting with another human being, we've got jillions of quantum processes going on, and you've got, it's just not a pristine situation. Could you count on that non-locality? I mean, in a certain sense, since remote viewing works, you could say, well, there's non-local access, so non-locality is actually occurring.
What about those experiments with rabbits where they took the babies away from the mother and they did something to the babies and the mother reacted because there was this, you know, biological non-local connection? Have you seen those studies?
Well, I've seen them reported. It's not clear whether it really happened or it was a myth.
Well, then, when you...
I have another question. I mean, I'm curious about the levitation experiments, and I'm also, you know, the people that can do miracles, somehow they're piercing the veil between here and there, and on a physics level, how would that work?
I wish I knew.
But
what we need to do is to, you know, have somebody who could, in fact, I mean, obviously, what would the physicist like? Miracle worker, come into my lab. Okay, let's perform some miracles here. And okay, now I see what you're doing. Okay, let us set up our instrumentation. I'll perform the miracle again. You know, we could get from here to there if we had that kind of access. But you know, in cases where people apparently have miraculous events kind of occur, they're kind of spontaneous, so they don't have them under control. Or even those who have them under control to some degree may not be at all interested in, quote, demonstrating it to those stupid scientists who are only interested in numbers.
okay, here's my last question. Are any scientists interested in cultivating those same techniques that people who perform miracles like swamis and things like that in order to be able to recreate them?
They're few and far between. Actually, Brian Josephson, Nobel laureate, known for the Josephson junction, which is a superconducting effect for which he got the Nobel Prize, is also a transcendental meditator and deep into the cities program and so on. So, and he tries various kinds of experiments to try to connect up the science he knows, which is very profound, and the experiences he's having. And so there are a few out there. And sometimes he attempts to publish them and usually gets rejected, but the word gets around anyway. So few and far between do you have somebody who's wearing both hats. He happens to be an example that comes to mind.
Well, you are, because, I mean, you even quote Arthur C. Clarke that says, you know, the physics of tomorrow will seem like magic today.
Right.
In that quote. So, I mean, the whole idea of wormholes where you can open up a time-space and slip into another part of the universe.
Right.
That's a possibility.
That, general relativity, if the equations are right, that's a possibility.
I mean, how does that actually work? I mean, how can you actually, what do you need to do that, to open a wormhole in basic layman understanding?
You need a lot of energy.
Yeah.
That's one thing you need. you need to structure it in a certain way so as to affect the vacuum. We can write the equations for it, see how it is. It's a little hard to describe physically. I mean, actually, we don't really know how to actually go out and do it physically, because there are few little things like, oh, I'm going to need some negative energy here. Where am I going to get some negative energy? Well, in some sense, the Casimir effect is actually considered a negative energy thing. So, okay, maybe I want to have Casimir walls around my wormhole, and so we see the mathematics of it, can predict that if general relativity is right. I mean, this is enough to make some people say, general relativity must be wrong if it predicts that. And there are some other models that, more or less match general relativistic predictions, but don't have that effect in them. So actually, at some level, it's still sort of controversial where you could do it. But the way the math in general relativity, Einsteinian general relativity is now, it predicts you could do it, but it would just take enormous amounts of energy.
Stephen Hawkins goes into this in one of his new books, not Brief History of Time, but the next one he put out. But he has a whole chapter on this.
Right. Yeah, it's among general relativists and cosmologists, they take it seriously. It does get published in, Matt Visser, one of the leading wormhole theorists, just published an important paper in Physical Review Letters, which is the toughest journal to get into, where he had just done some calculations where he showed that whereas we thought we needed a lot of negative energy, we can actually get by with just a little bit of negative energy. But of course, we still have to figure out where to get negative energy from.
Or maybe those anti-proton colliders. But just imagine what Einstein could have been intuiting when he created that. Can you get into the mind of Einstein and see what was he thinking in order to come up with these ideas? Have you been able to do that?
Well, now since we're treading old ground that has been elaborated for 100 years almost, or at least 85 years in general relativity, we can pretty much get into the mind of what he did. Of course, he did it in just 10 years of thinking about things very intuitively. As he describes, he imagined himself riding on a photon away from a clock, and the clock would appear to not change time. And so does that mean time depends on your motion? And so he thought very intuitively, and in fact, he was actually quite skeptical of mathematics. There is a famous quote of his that says, well, if it's mathematically totally tight, it can't be reality. And if it's reality, we can't be mathematically tight about it. And he hated learning tensor geometry, but he was forced to, given that that's the way his theory was going. So we can sort of reproduce and understand his thinking. It's no longer true that only, 10 people in the world can understand relativity. There are a lot of people.
And they're using it right now to do some of these experiments.
That's right. We have, for example, the prediction of gravitational waves. They're
using gravitational waves, right?
We've not yet actually seen them. As close as we've gotten is that we've seen two binary pulsars whose orbits are changing, and you can calculate how much energy they would be losing in gravitational waves, and you can show that the decay of the orbit matches the theoretical prediction. And for that, Taylor and some other people got a Nobel Prize. But we've not actually detected gravitational waves. Now, we just have coming online something called LIGO, Laser Interferometry Gravitational Observatory, I think it is, which has long legs. I don't know if it's kilometers long or whatever. A large interferometer whose sole purpose is to detect gravitational waves coming from astrophysical events. But no one's ever actually measured gravitational wave yet.
So it's still a theory. But teleportation happened with a photon. They have done that.
Yeah. Now the teleportation, as it sounds to a layman, is something was here, suddenly disappeared, and pow, suddenly it was there. It isn't exactly like that. It's that you had a photon that had certain quantum properties, and and suddenly those quantum properties were able to be reproduced over here. So, and since the only way we know about a photon is its quantum properties, then you might as well use the word, well, it teleported from here to here because whatever was here is now here.
Well, how did those properties go from here to there? What was that mechanism that got them there?
Actually, that's not an area I'm particularly familiar with. I mean, they're very, pristine experiments. I mean, they do not imply that it's photons today, insects tomorrow, frogs the next day, and people following. So it's a very pristine kind of environment. I'm not really up on the details of it.
Right, but the warping of space is something that you can see definitely is possible if we get enough energy. Yeah.
Well, in fact, it happens already. I mean, we do see starlight bent by the sun as it goes by. So natural things like the sun already warp space. And so it's a case of, well, gee, if I had the mass of the sun in my pocket, I could cause light to bend around me too.
Right.
So we know in principle, and we see in practice that it happens. The only question is, well, what can we do to do it on, say, a laboratory or spaceship scale?
Right. So the mass and the generation, and also in remote viewing and all the psychic energy also affects mass as well, right? I mean, there's that phenomenon, like very tuned in people, like Swami's, affecting things around them.
Well, in principle, I would think that's true, and in that particular case, since I happen to be a bug about zero-point energy, its randomness, and to what degree it can be cohered, I have as a hypothesis that a very intense person or anybody at an intense time may partially cohere vacuum fluctuations, and that could be measured. So maybe as technology advances and we have a lot of easy-to-use zero-point energy fluctuation meters, you can come up to a sort of magical person and say, oh, well, I can see that, you're about 6.3 on the ZP Richter scale here.
Well, Uri Geller, though, you don't have to tell that whole story, but he's a very intense guy with a very intense field that affects, he can bend spoons by touching them. I mean, probably comes off of some of that intensity.
It's interesting. In our own particular experiments with Geller, in the laboratory, we never got, under scientific conditions, what were acceptable scientific conditions for us, proof that he could do psychokinesis, although we saw many psychokinetic events around him on a casual basis. And I think that there were some experiments done at Lawrence Livermore Laboratory where he was doing something on a piece of metal that was being monitored very specifically, and they did see effects that they couldn't account for. So I think some other labs may have gotten some data, and in our particular case we didn't, but anyway, it would be compatible with the idea that vacuum fluctuation energy or some other form of space-time warp actually occurred at some microscopic scale.
Yeah, why not? Yeah.
This
I
test.
have a quick question. Why do you think it's so difficult to capture in the laboratory? It seems to defy scientific explanation.
There's so many sociological and psychological factors involved. He himself thought that, maybe the world wasn't ready for it, to have it really in their face, and that's why I couldn't do it. I mean, he gave some other analogies, like sexual analogies. Well, suppose somebody put a camera on you and said, okay, it involves the whole person and depends on the environment, and so in fact there are a lot of reasons to think why it might not be.
Well, actually, someone said that sexual energy is related to some of the PK energies.
Yeah, certainly we've heard that, and you read about it in the literature.
But what kind of stuff have you heard about that? What's the evidence? What's the association? Really?
Well, the association that I have heard from people who claimed psychokinetic events was that at the time they felt sexual. So it's a sort of a subjective.
Or maybe more energy running through their whole body in general, which stimulates all the organs, you know.
Right.
So, well, it's all very exciting. More, I mean, we just go ahead.
Yeah.
What?
I was going to say, if you want to close it. Or...
No, I mean, John has one more.
The second law of thermodynamics, inviolable in space-time, but apparently in quantum energy, it doesn't apply. There's no real translation from order to disorder because it goes back and forth.
That's right. It's a new area actually in thermodynamics that people have recognized that the second law, which basically a law just says everything kind of runs down and gets more disordered.
Right, with entropy.
Higher entropy states.
Entropy
In certain quantum
increases.
systems, under certain conditions, there are violations of that at some level. And so this whole thing about quantum thermodynamics is a new area that just the past year there have been a couple of papers published.
If you have a zero field, how can you define entropy? Because energy appears and it disappears. There's no.
That's right. Really, thermodynamics, as we usually know it and love it, is really a classical concept that applies easily on the classical level. It only has to do with the statistics of having a bunch of things that are well defined, and you statistically randomly mix them up and like shuffling a deck of cards. By the time you get into the quantum level, where you've got indistinguishability between particles and they're there or not there, I mean, the rules do change.
Well, indeed, in a closed system, entropy perhaps works, but in an open system, which seems like we live in that kind of universe that's always being influenced by this vacuum, this quantum fluctuations, we have an open
Well, that's
door
true.
universe.
Certainly, Prigogine got his Nobel Prize for pointing out that, and a human being is a good example. I mean, we are ordered in our environment as compared to just random molecules floating around. But it's because part of that requirement is that there is open access to energies, that we are an open system.
Yeah.
So that's true. From the standpoint of a zero-point energy theorist, everything is an open system.
Right, and it seems like even perhaps the theory that suns are dark holes in some other universe that are pouring out light. Have you heard that one?
Yeah, the black holes here or white holes
Yeah,
somewhere else.
right, I like that
that's-
one. Do you think that's a possibility?
That's a possibility. I mean, these days, almost no matter what you would say to a physicist, he's got to say it's a possibility.
Right.
Because physics is just expanding like that.
Right. Well, thank you so much for all the work and intelligence and passion you're bringing to the field of physics. And
Thank you for